The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
Welcome to the Into the Impossible podcast, a production of UC San Diego's Arthur C. Clarke Center for Human Imagination. And it's a real treat to have one of my heroes, my heroines, however you want to say it, in physics. And not only a physicist, we have a lot of physicists on this show, but an experimental physicist. And you may be one of the first, if not the first, honest-to-goodness experimentalist who has come on this program. So thank you, Elena. It's a real treat to have you here.
Such nice words, yes. That make me happy.
I'm glad. You make a lot of people happy.
To think about me as a woman and an experimentalist.
Yes,
I like to do things with my own hands.
Yes, absolutely. And it's wonderful to have you here. I want to give a brief introduction for the few people out there who may not know you. You were born next week in a time that I won't mention, but your birthday is March 12th, which is only 2 days before Einstein's birthday. So that's wonderful. And unfortunately, Stephen Hawking's date of being deceased was March 14th, I believe. And she is an Italian-American particle physicist. She's been a professor at Columbia University since 1986. She's the founder and spokesperson of the XENON Dark Matter Experiment, which is a major component of our conversation today. She's known for her work with Nobel gas, Nobel liquid detectors, and her contributions to particle astrophysics, in the particular the search for dark matter, which was the subject of your visit or your talk that you gave to the public as part of the Arthur C. Clarke Center for Human Imagination. We screened a film that you're in, so you're not only a wonderfully accomplished physicist, a professor at a top Ivy League university, but you're also a movie star. And I think, I mentioned to you earlier, my wife thought I was interviewing Sophia Loren when she saw the film last night. But I do want to just mention your brief background. You were a student in the University of Naples. You were at Harvard in the 80s, working as a postdoctoral researcher for Carlo Rubia's group, who's a well-known Nobel laureate, and the subject of a book called Nobel Dreams. And I'm not sure if you make a cameo in that book. You may not. I forgot.
Well, I'm crying liquid argon tears in that
book.
It's true.
So she's had so many awards, but though I'll focus on one of them. She's NSF Career Award. She received a Medal Ufficiale della Repubblica Italiana from the Italian president, Carlo Azeglio Ciampi. She has an asteroid named after her, so that is a type of dark matter which is named after you. It's asteroid 268686 Elena Aprile.
No way.
Yeah, discovered by Italian amateur astronomer Silvano Casuli in 2006.
How do you know that?
I know it. Check Wikipedia, folks.
Oh, gosh.
She received the Lancelot M. Berkeley New York Community Trust Prize for meritorious work in astronomy from the American Astronomical Society, and she is gracing us this quarter at UC San Diego as one of our Margaret Burbidge visiting professors. So welcome again. I want to talk about Margaret Burbidge because the visiting professorship that you hold currently is named in honor of my colleague Margaret Burbidge, who is 100 years young, and she lives up in the Bay Area of California. But she is one of the founding members of the Center for Astrophysics and Space Sciences, where we found ourselves today. And among many of her distinctions, ranging from not the royal astronomer, there's some controversy about that, but she was the astronomer who led the Greenwich Observatory. She was president, I believe, of the American Astronomical Society, many things. She was one of the leaders and founders of this center that we're in now. But she also, among her many honors, she trained in some sense and befriended a young astronomer by the name of Vera Rubin. And of course, Vera Rubin is well known as being credited with finding some of the most convincing evidence for the existence of dark matter. So I wanted to just highlight that fact that UCSD has this deep connection through Margaret Burbidge and Jeff Burbidge, her husband. The two of them were very close with Vera Rubin and her husband. When she did a sabbatical here in the 60s, that's when she learned a lot about the type of spectroscopic studies that she could later use to measure rotation curves of these distant galaxies and really provide some convincing evidence for the existence of dark matter. So I want to ask you first, what is it about dark matter? Why does it transfix the imagination? Is it the name? Is it this mysterious properties that it has of seeming non-interactivity? Because I know a lot of people who don't like to interact are very introverted, but dark matter seems to be quite introverted in a sense. What fascinates people? And maybe I'll ask you, what interests you the most about dark matter?
I think simply is because if you think that the stuff that we know makes such a little amount in this universe, it's just, how can you not think about finding out what the rest is? So I don't know if the name is correct, this dark matter. I mean, we inherited from Zwicky, right? But what is it about it? I think we have to do it. I mean, there is no other way. I mean, it's so important because when you tell your children or your friends, I mean, what are you doing? You're studying dark matter. And the way I usually present it is that we're trying to find out what the 95% of the universe is made of. And they say, what do you mean, what the 95% of the universe is made of? Because, I mean, for normal people, this is an intriguing question. But for us, it's much more intriguing because the connection about dark matter and what it is and particle physics and what we learned all this life about the building blocks of nature and the fundamental laws of physics, all that can change once we find out what this dark matter is. So it's the connection, for me, is the connection with astrophysics, astronomy, cosmology, particle physics, which actually is the most appealing. I cannot think of another topic today which unifies all these disciplines.
Right. And I guess, some of the question that naturally comes up is dark matter a new type of material? Is it actually matter? Or could it somehow be, a placeholder for some ignorance that we might have about how gravity works? Can you say something about whether or not this is still a deep controversy within your field?
I wouldn't say it's a deep controversy, but we have had modified gravity theories, and we have more recently heard about this a new theory of gravity from our friend Eric Verlinde. So it's not a controversy, but there are people out there who might, and I don't know if they're correct, we don't know. It's plausible, but any new theory would have to explain all the phenomena that we see and observe. And as far as I know, to date, none of these theories that some of these people have put forward are able to explain fully the observations that we have at all scales. So until then, I'm just keep looking.
There's sort of a thorny issue that I've thought about a lot, which is how do you know when to stop doing an experiment? When we teach our undergraduates, there's a known answer that they're trying to get, and they stop when they get something that's reasonably close to that answer, or could conceivably convince their TA that they're on the right track. But before we get to how do you turn off an experiment, which I think is an interesting question in the context of pursuits where there may not be an answer. We may never detect gravitational wave B modes in the CMB, for example. Maybe it will be impossible to detect dark matter. Who knows? But we'll talk about that in a minute. But before that, I want to talk about how do you decide to start an experiment? What gave you the chutzpah, as we say, the gumption, the gall, if you will, to start this incredibly ambitious, many tens of millions of dollars experiment that you've raised with your collaborators? And what gives you the notion that it's time to pursue something and start off on something that could be a 20, 30, 40-year quest?
Well, that's easy to answer because when I started, which is more than 15 years ago, the field was so way back different than now. The situation was quite easy in a sense because we had had few detectors, few technologies, very, very powerful, but small-scale detectors, and they were searching specifically for this hypothetical candidate for dark matter, which we call the weakly interacting massive particle. So designed specifically for that, to measure the tiny energy that would be released in a material if this hypothetical particle would care to scatter off an atom of that material. And so we were talking about these beautiful cryogenic bolometers at that time, and they had explored a little region of this so-called parameter space, namely the interaction strength of a WIMP with a nucleon. And at that time, these technologies, the scaling up of those technology was already clear then that it was very painful, costly, and technologically very challenging. So I happened to attend a meeting at the SNOMAS meeting in Colorado, I think it was. And I listened to a lot of these dark matter talks and saw the picture of the status of the art at that time. And I connected quickly to the development that I was doing for NASA for gamma ray astrophysics. I had been developing these liquid xenon detectors for detecting the radiation, the nucleosynthesis from supernova, from nova. And so I decided, or I thought that my detector would be actually better and more scalable than this technology of the time. And that's how I got the idea of proposing the XENON experiment.
So, and if I'm not mistaken, you have a patent related to that gamma ray astronomical
Yeah,
work,
that was
which
with
is-
one of my graduate students. It was a light detecting device. We did a lot of work in the lab with these noble liquefied gases, and so then I settled onto liquid xenon, and a lot of the work was done for, as I said, as a Compton telescope, to use it in a Compton telescope for imaging gamma rays from, let's say, nucleosynthesis in stars.
And what is xenon? How does it compare to, say, helium, which you can go down to the supermarket and buy a balloon full of? What is liquid xenon?
Yeah, I know,
what
and
is-
you like helium. I know you do, but we have had hard time to detect electrons in helium or to actually see scintillation from it. So the advantage of xenon and all these rare gases is that it is the most amazing in terms of when you cool it down, when you liquefy it, in terms of ionizer and scintillator. So it gives you the highest yield, the largest number of photons per unit energy, of free electron per unit energy. That gives you signals that you want to have available to detect some radiation. So it's a great radiation detection medium. It is, in addition, very easy. I mean, with time, after 15 years now, we learned how to make it clean, to remove electronegative impurities, stuff oxygen-like, which eat easily electrons, and if you lose the signal, you know, we're talking about a handful of electrons when we talk about detecting the energy of a dark matter particle interaction. So even few electrons lost is detrimental. So we need to keep this material clean. We learned how to do it. The other advantage compared to, let's say, argon or helium is that when you liquefy, the temperature is relatively warm. So as I say sometimes, easy cryogenics compared, let's say, to what you're used to.
Right.
So we have invented cryocoolers, pulse tube refrigerators, which can keep this xenon. In my lab, we used to be in small detector size. We used to use nitrogen and alcohol and make a molasses. I would steer with the wooden stick. So it's hard to keep a detector for years and years if you want to steer the thing. So mechanical coolers have come very handy, and we have made a lot of progress on that for that specific liquid xenon temperature. Let's say minus 100 degrees or so C, because most of the cryocoolers you find on the market are optimized for liquid nitrogen, typically.
Right.
So for liquid xenon, we had to develop with a company in Japan a specific cooler, pulse tube refrigerator. So it's very good ionizer, scintillator. You can keep it clean. And then for dark matter or rare searches, another great advantage or requirement that you have is that there are no intrinsic radioactivities, because you're searching for a very rare event. If you have, the example is the argon. Liquid argon is also a very good candidate for dark matter as target and detector medium. But you have the big problem of the argon-39 intrinsic radioactivity, which gives you a becquerel of rate. And so, of course, we have solved that as well today, because we are trying to extract this argon from wells and remove this intrinsic radioactivity. In xenon, you don't have intrinsic radioactivities other than maybe the krypton, traces of krypton. And we have learned again with time how to distill. We say distill, yes, cryogenic distillation is being used a lot. We have huge distillation column on the xenon setup to remove the krypton, let's say, because krypton has this tiny amount of krypton-85, which is radioactive.
Radioactive as well, right?
So all these things make it, and also I think, coming back to helium, you have to see also where most of the work went.
Yeah.
You know, Because still today in my lab, in many other labs, we are learning about the fundamental physics, the microphysics. Sometimes we say, oh, this liquid. We still have a lot of things we don't understand. The recombination process, because the mechanisms through which these light and charges are produced in these materials are quite complex. There are interplay between applying an electric field to keep the free electrons separate from the parent ion, stuff which eats the scintillation, and the excimers which are formed and go to ground state giving you light can be formed also through the recombination process. So it's a very complicated physics, and also physics that we had to learn to find out very low energies.
Right.
Because the work I did with NASA, within the NASA framework
side,
of thing was MEMeV energies, the famous 511 kV line. And now you're asking, what is the energy that
Dark matter.
a nuclear recoil from a WIMP interaction gives you?
Right.
And this is few kV.
Kiloelectron.
And so the first question I had when we started Xenon was, how many electrons do you expect from a kV of a nuclear recoil?
recoil, right?
Which I didn't know because I was dealing with gamma rays, alpha particle. What is a nuclear recoil?
Right.
So we started to make experiments with neutrons in the lab to produce a nuclear recoil from neutron scattering on xenon, and measuring the yield, how many charges, how many photons you find in these detectors, in order, essential question to calibrate.
Yeah.
So, and we still haven't finished this quest because, of course, we want to go lower and lower in energy.
Right. More resolution.
And so on and so forth. But as an example, I bring always my proposal, the Xenon proposal at a threshold, I don't remember, 10 or 20 kV as an energy threshold. When we first did the first prototype, even Xenon 10, we could show that the energy threshold was much lower than that. And the reason is that we had no idea that we could go so low. I mean, nobody knew really how low in threshold. But now you know these detectors can be a single photon sensitive, single electron sensitivity. So that's something you learn with time.
So the current limits that you have achieved with xenon are really the most competitive in the world, I would say. Although we should say, and maybe I'm curious because I can't resist. I have an expert, and an Italian expert, no less. What do you think about this Dama excess that's been going on since I was a graduate student? That seems to suggest that there is not only a dark matter existing particle, but it behaves exactly as you'd expect from the sort of distribution of dark matter particles in our galaxy, and the relative increase or decrease is sort of a wind, and running into the wind and out of the wind as the Earth orbits around the sun each year. And getting the so-called annual modulation. So this is a many sigma. I forget how many it is by now, but the claim is that
it's 12 or more.
12
yeah,
or
we
more,
had
maybe
a talk
13, right.
a few weeks ago again at this conference.
So
It's
you're
the
the
same
world's
talk.
expert. Yeah. So tell me, what do you? Yeah. When I was a grad student, it was 5 sigma. Or
They have
something.
increased their significance of this modulation. They clearly see a beautiful signal which modulates with the right phase, and it just remains as of today unclear what the hell is doing that, because if that were coming from the vanilla WIMP hypothesis, the same WIMPs that we're looking for in these detectors and many others, based on that rate, on that amplitude, we would have to see a huge signal, which we haven't seen. And so the only way to answer that question, modulation is indeed the most direct and beautiful way of discovering a WIMP. And so for that, we have actually made a search with our own xenon data, xenon 100 data, to search for animodulation and test for leptophilic models and whatever. We still don't find anything. So the question is, why is it so special, sodium iodide, which is the target that this experiment uses? And after so many years since I started myself, we have finally come to the point where we have other experiments using that same technology, testing the Dama signal. Unfortunately, these experiments as of today, they haven't reached the sensitivity or the statistics good enough to say yes or no, so they keep taking data, and I'm waiting. We don't find these signals in Xenon, we don't find it in other detectors, so it remains a mystery. And so we don't go there, they insist, but if I were the dumber people, I would have taken my detector and moved it somewhere else.
the southern hemisphere.
Or give it to somebody else to take some data and analyze the data.
My
But
understanding is they're a little
they're
bit more...
very stubborn on keeping their...
Yeah. So is it natural not to be stubborn? One of the things that was so resonant with me in the film Chasing Einstein, which is your one of your debut. It's probably your debut on the big screen, and a wonderful documentary which is available for people to purchase online, iTunes, YouTube, etc. And they cut to you and they show you, along with some, I guess you're listening to Shakira in the background, very elegant, very, and they show you, and then they show you going into the lab, and you're in the lab, you're with your students, you're clearly at home.
Morning. Hello. The wiring was you. I was screaming at the other girl, the other student. But you left it around.
And you say a lovely thing, which, again, resonated with me very strongly. And you say, "This is my baby. This is my baby."
This is my baby. And I love it every time I come in here. My students, sometimes I shout. I scream and shout, really. I hate to see those cable ties left hanging, and I'm sure you find some. If your cable tie is hanging, it means in your house you also. And who is going to want to have a guy like you? So I keep telling them, you have a better chance to find a woman. XENON has been operating for more than 1.5 years now, so we're very close to open that box and see what nature has for us. You want to be confident and excited and hopeful that maybe this time is the time and you will see a sign of dark matter.
It spoke to me in that this sort of personification or anthropomorphizing your experiment, which is something, we all bleed, cry, and sweat on our experiments. And I don't think the average, layperson appreciates just how hard it is to do these results, especially given the fact that we seem to come up, at least from some perspectives, of null detections, of no positive results. We have not yet detected, as I said, convincing evidence for, inflationary origin of the universe, if you will. We may never, and it may be that inflation did take place, but we don't have the sensitivity and never will. Or it could be that inflation didn't take place, and there might be some other alternatives. How do you continue to persist in the face of this? So the Dhamma folks clearly feel they have something to prove to the community, and that they are not being accepted at face value. I don't know of any other field where such a large statistical significance would be dismissed. But so where do you get your when do we get, as experimentalists, when do we realize it's time to wrap up?
When I started, the field was a certain stage, and it made a lot of sense to jump in. And in fact, the major achievement that I feel I've made with my collaboration and experiment is really to explore not one, not two, but 4 or 5 orders of magnitude from where we were then, in terms of testing the interaction strength of WIMPs with matter, excluding cross-sections which are lower, lower, and lower. 4 or 5 orders of magnitude in about 10 years, 12 years. This is a major deal in this and any other field.
It's huge swaths of
And now
space.
we are getting to the point where we are making these detectors more and more sensitive, larger and larger. There where the scalability vision that one had, everybody knew, but you have this noble liquid, you can make them larger. We're talking about not few tenths of a kilogram, we're talking now about 8,000 kilograms. 10,000 kilogram of target, which has never been done.
Right.
And with that kind of step, now we want to seize the last little bit of this so-called theoretical prediction. We are basing our detector. The detectors have been designed specifically for a particle candidate, which is called the WIMP. So all these detectors have been designed specifically to search for mostly massive WIMPs. Search has been done mostly for tens of GeV, hundreds of GeV, up to the TeV scale, massive WIMPs for which this target, specifically xenon, is very, very good because it has a lot of nucleons. The xenon atom is very large. And if a WIMP scatters off a nucleus, it likes to scatter with all the nucleons coherently. So the larger the nucleus you have, the better you are off in the spin-independent so-called way. So now we reach the point where we're going to exclude maybe just one order of magnitude. We are separated from a level of background that we can't avoid, despite all our smart, which is the neutrinos.
Neutrino background.
And so neutrinos from the sun, from the atmospheric neutrino, the supernova neutrino are going to give us a signal soon. But we have that last one order of magnitude, maybe 2 orders of magnitude, separating us from the signal of neutrinos. And so I think at that point you have to stop, in the sense that you turn your detector into a beautiful neutrino detector, but there are many others. So the natural stopping time is coming to the time when the neutrino signal is going really to make it impossible for you to find a signal from WIMP, if it is so at the level of neutrinos. So but we still have a way to go, because with the current generation of experiment which is about to start, the XENON and TON, we're going to go still an order of magnitude above the neutrino floor almost. And then if we're still finding nothing, there is a little bit more and a lot of pain to get there, because it's amazing how you scale them up, but you gain very, very little.
Yeah, exponentially small.
And then at a certain point you have to stop, because, I mean, you can't even distinguish these particles, if they exist, from the more known expected particles, such as neutrinos. So we do know when we will stop. I will stop then.
Yeah.
Maybe I'm still hopeful that in the next round, which still is going to last 4 or 5 years from now, of searching for about another 4 or 5 years. So this decade for me is going to be critical, because we are going to start to search competing alternative experiment with the same technology starting, and we're competing to start at the same time. We will have a liquid argon as well experiment starting this decade. The LHC is starting again after this shutdown. We have indirect detection with these beautiful telescopes from IceCube. The Fermi is still out there, and we have EMS out there. So again, we said that last decade, actually.
Yeah, exactly.
I know, we keep saying the same thing, but we are going more and more down.
Right.
So in terms of theoretical framework, I mean, of course, our friends theorists are so smart, they'll keep coming up with alternative.
Right.
And you know very well already the absence of a signal in all these channels, from direct detection, indirect, direct, has prompted a wealth of searches in neighboring energy regions. So low mass WIMP searches with accelerator, with beautiful little technologies, because the cross-section shoots up at low mass, so you don't need such large detectors. And we have a lot of effort going on at low mass. And so eventually this decade, again, at least from the direct detection, which is the most, in my opinion, direct way of finding this particle from the halo of this galaxy, should be concluded. Because if we still don't find it this decade, there will be very little separating us from the neutrinos.
Okay, well, in March of 2030, you and I are going to be back here, and I'm going to
we
hold
will
you
talk
to that.
about how beautiful the neutrino signal is.
Or the dark matter signal.
Oh, the dark matter signal.
So, I mentioned that I have a favorite quote. Comes from Oscar Wilde. He quotes in a book, or his writing, Lady Windermere's fan. He has a character, Lord Darlington Quip. The definition of a cynic is a man who knows the price of everything, but the value of nothing. And I think it's sometimes hard to convince people, when they ask me what I'm looking for, and I say mostly nothing, or static, or whatever.
Noise.
Noise, yeah. We spend all our days looking at noise and trying to get rid of
understanding noise.
And trying to understand it and model it, etc.
Reduce it.
I think that's one of the popular misconceptions of scientists. First of all, they think we all have beards and we are rubbing our beards, and that's obviously not true in either one of our cases. But I think there is this sort of impression that it's only science if you make a discovery. In other words, sort of positivist. You have to actually have something clear rather than ruling things out. In the film, there's a young physicist postdoc who says, every paper should be celebrated like a triumph, like a victory.
He was a great it was a great quote. So,
Yeah, and I think there is some value in that. I think there is this tendency to look at people like Einstein, who's the film namesake character in Chasing Einstein, and kind of hold him up to this level of authority and sort of almost like a halo effect that nothing that he did could possibly have failed and been wrong. And in fact, as we know, he made many blunders, and some say he made more blunders than actual successes. I don't know if I agree with that. I think he, as I always say, he could have had a good career if he didn't. But a lot of what comes up in physics is serendipitous, and we don't expect it. The discovery of the cosmic microwave background, the CMB that I studied, was completely serendipitous.
Yeah, that's a beautiful one.
The discovery of the acceleration of the universe, of dark energy, that was also serendipitous. They were looking for exactly the opposite. And I wonder, if by focusing, maybe this is just too philosophical to get into, but discoveries of, your countryman Galileo Galilei, he discovered things completely by accident and then applied scientific, principles and the scientific method towards sussing out all the details of that new field that he had basically single-handedly invented by virtue of this exquisite technology that he pioneered. And I see similarities with you. You pioneered this tool, you've vacuumed up all of this parameter space, and that's sort of a natural thing to do. But I worry, I wonder sometimes if what's driving us. Galileo never really released the plans for his telescope so that even his friend Kepler could reproduce it, because he wanted to keep making these low-hanging fruit discoveries himself. And I wonder, is that driven by this competition? As you know, my book, I focus a lot on competition and whether or not what role the Nobel Prize plays. In fact, in the film, you open in your office, I guess. I haven't been there yet. I hope to someday visit you in your office. But with a poster of Marie Curie, and you talk, the first thing that comes out is about the Nobel Prize and how she won 2. And I wonder, is that a motivation for you? I know your advisor won a Nobel Prize, and obviously it's a very dominant theme overarching both of our fields. Does it play a role in you personally? Is it something that influences you personally?
I have to say no, to be honest. We are embedded in this idea that, of course, that's the highest honor you can get, and it would be absolutely great, it's true, but it never played a role, I have to say, because actually I see that when people get the Nobel Prize directly, I had 2 good friends, from Rubio to George Harpag. I was very close to these 2 great scientists, but they change completely. They get completely paranoid and crazy.
Yeah, right. Now they
so
say,
I don't like it.
That's right. I think T.S. Eliot said the Nobel Prize is a ticket to your funeral because you never do anything good after you win it.
I don't know, so I don't look forward to that. But of course, the statement I made about Madame Curie was very natural because, well, she's known, or she is the first woman and the one who got it twice. So, but such different times. And I wonder, I don't know how she behaved after. Probably she was still normal.
Yeah.
I am more proud about seeing Madame Curie more in reading some of her biographies about the real woman.
Yeah.
Because we tend to forget that the scientists like you and me have a life.
Yeah. Let's talk about that. In particular, both of us are parents of daughters, and I know that that in addition to Margaret Burbidge and Vera Rubin spending some time here, Maria Gephardt-Mayer was here. And when she won the Nobel Prize, her son told me that the newspaper said La Jolla housewife wins Nobel Prize.
You see?
And I wonder, how do you think of yourself? Are you a scientist? Are you a mother? How do you picture yourself as a human being? What defines you to you?
I am what I am. I am a woman, and I happen to like to be in the lab and to build great technology instruments, and I am most proud of my daughters because that's, I used to say, and I wrote it down, they are the best experiments I made. The most successful experiment I ever made. Yeah. And I would never do anything differently. Of course, you still feel guilty about the time you took away from them because the lab doesn't have time.
Birthday parties. And
the birthday missing. But they knew, and they grew up stronger by knowing that his mother has always something on her mind. She's thinking while she's cooking.
Yeah.
But to me, and I want to instill in every young woman and student today approaching science that they can do the science. They have to do the science, but without forgetting that they're women. And caring to find a guy or whoever they want and be happy in the rest of their persona, make babies, because I mean, I think that every woman should have that experience.
That's a superpower that women
I
have,
mean,
right?
and I always felt that how do I feel? I always felt stronger than my colleagues. I was the first woman in the physics department of Columbia.
That's right.
So a lot, you can imagine, I've been always alone in these meetings, very, very much alone. So I'm vaccinated. I never cared though,
Right.
because when I then got pregnant of Julia at Columbia, I mean, the people who had problems were more my colleagues than myself, because they were not used to see.
Right.
And the bias is large. I mean, what are you doing here? You should be home resting. And I say, no, but I'm fine. I'm feeling
don't
good.
tell me how to rest.
I'm feeling good.
They're not that kind of doctor.
I mean, I have no idea. But, you know, you have to keep going. And these young women today have to know that women, like the Vera Rubin and I'm sure Margaret, I mean, women can have a life and be a great scientist.
Yeah,
It doesn't have to exclude, one doesn't have to exclude the other.
Yeah. And I think
It would be a pity. In fact, what I find most sometimes sad is to see colleagues, smart women, who actually made a choice or made renouncers and didn't decide at the right time to fulfill other dreams in their life, and then eventually
you can't.
they regret, and then it's too late. And so I think we should encourage.
Yeah, I always say it's the hardest possible thing you could do, and I'm speaking as from a male perspective, but you know I know it's a lot harder. But being a parent is, you know, it is an experiment, and you hope that they're not null experiments, and that they yield good results. I have to say that I am, you know, you would enjoy coming over and helping with my twin 1-year-olds because they produce a lot of dark matter in their diapers, so you'd have firsthand experience, direct experience. So there are a lot of ways we could go with from here, but I do want to just maybe close out the discussion with one of the ways that you inspire physicists like me is as a leader, and it's something interesting that kind of relates back to Einstein. So, you know, Einstein was asked to be the first president of the new nation of Israel, and he was like, "Why should I do that?" And they're like, "Because you're smart." But really, there's a halo effect where people think, you know, if someone can do one thing, that it translates immediately over into some other discipline, which it doesn't. But you've managed to do two things that are totally different, right? To excel in your branch of physics, and to also be a scientific manager and a leader. And there's I think it's almost harder to do that. As I say, you know, as I said earlier, it's not like herding cats. At least cats basically stay on a planar surface. But, you know, butterflies or herding neutrinos or dark matter WIMPs. How did you do that? How do you do that? What are any tricks or skills?
And you know, I didn't learn any management skill.
No, we
don't.
And
I think some people have it better than others. I mean, I thank my mother for that. It's that intuition that we have in understanding people. I'm reading people, right? I don't take very long to figure out when to talk to you in certain ways. And so I managed to keep together this collaboration, which grew from 20 people to almost 200 people. And I'm still managing that, but the way I do it is still my own way. Sometimes I go a bit off the tangent, but typically I use my so-called intuition, this connection that I have with people. I can read very easily, and
motivating.
Definitely I'm motivated. My students are my babies. I mean, I care a lot about every member of this collaboration.
Yeah.
And you see a lot of your colleagues usually treating their students like someone who you can see only once a week, maybe once even a month. For me,
that much? Just kidding. My students out there.
I know.
I'm just
I'm
joking.
saying, for me, it's everyday life. I see it, and I want to know everything what they do. I'm so it's true. I always am curious, but the reason why I'm curious, how are you doing? How is it going with your wife? How is your kid? My poster. It's because I know, first of all, it's probably selfish.
Yeah.
Because somebody happy works better.
Yeah.
So when I sense that something is wrong, which is a personal matter, I try to help them solve it, because I know that otherwise there's an impasse. So it's also a bit selfish, but I do care about what they're doing with their life as well, and try to help them.
Yeah.
And try to help them also become not just great scientists, but also great human beings. And if that means also learning how to make a good espresso.
Yeah.
And how to cut cable ties.
Ties, that's right.
So that the woman will not think of them as sloppy.
Right.
I mean, that goes without saying.
That's
For me,
right.
it's important to And we will have workshop on how to make the best lasagna.
Oh, that well, I will
I
sign
mean,
up
even
for that.
that.
I'd like to
Well,
participate
I mean,
in that
how
experiment.
can you be a good physicist
If you
and
can't-
hope to get a great woman if you don't even know how to cook a good meal for her?
Very, very true. So my final question is a question I ask everyone, from Nobel laureates, Pulitzer Prize winners, entrepreneurs, etc., who've been so gracious with their time as you have with yours to come on this podcast. And that is, we focus here at the Arthur C. Clarke Center for Human Imagination on this question of imagination, which is naturally connected to creativity. The unique human capacity for reason, I think, is what sets us apart, what distinguishes us. But the question of, pedagogically, can you teach someone to be the next Elena Aprile? I mean, can you teach somebody to do the kinds of things, the skill set, the meta skills that we need to be the successes in our field? Is that a teachable skill, or is it you have to be born with it? Obviously, lasagna you can teach, but some like cuisine I wouldn't recommend on anybody, even if you were my teacher. So, is it something? As a physicist, can you teach someone to be a physicist? A lot of theoretical physicists say, I've interviewed, have said, well, we tend to think of everyone in theoretical physics as Einstein, and so I can't be like Einstein, so I won't even try. But we're experimentalists. We're dealing with the real hardcore substantive life and actually contact with nature, not only, and I'm not disparaging theorists, some of them are my best friends, but can you teach creativity? Can you teach imagination that allows you to be successful in our field of experimental astrophysics?
No, Brian, you cannot teach someone to be creative or to be imaginative. That's really something that you have. But you can help a lot, whatever is the little bit that you have in someone, channel it in the right direction. But I have seen over and over with my student, my postdoc, you can make them better, but if they didn't have to begin with the curiosity, the creativity, they're never going to invent something in the lab. They're going to be more follower than leader in that sense, but not leader in terms of taking initiative and making something new out of nothing. At least my experience has been so far that it's hard to teach. That's not a skill.
Yeah.
You can teach them to be great experimentalists. I have turned the best theoretical physics student into good experimentalists. But usually I don't get from them that innovative thing that you get from someone who is really, as I say, a lab animal.
Yeah.
That's like,
Right.
I have had a few lab animals in my life. And I'm not as good as some of them, but you really see that is something that these people just have it.
Yeah.
They just get better and better at it, but you can't beat that. You can't teach
There has
that.
to be something innate.
But maybe I'm wrong. No, definitely.
Well, Elena, it's been such a pleasure having you on the Arthur C. Clarke Center for Human Imagination's Into the Impossible podcast. I want to encourage folks to subscribe and like and review and rate on iTunes and elsewhere, wherever you get your podcasts, wherever you watch online, on YouTube and elsewhere. Elena, anything you want to promote? You're going to be giving a colloquium here at UC San Diego in April, I believe. We can't wait to see that. We just had our public event. You're around as the rest of this quarter as the visiting Margaret Burbidge professor. Anything you want to talk about that we didn't get a chance to cover on today's podcast?
I just wish here, like I do a bit at Columbia, but to a certain extent less, to encourage every student. I've been meeting with the undergraduate of women in physics. I will meet with the graduate students in physics, women in physics. But every young man and woman who is in love with physics to come and see me on campus while I'm here, or talk to me, because I think the future, of course, like in everything else, is in these young minds, and we ought to give them whatever we have learned, because as I grow older, you realize you have a lot to tell, to share with the younger people, of course. But if you don't have a chance to talk, you will never be able to pass the message.
That's right.
So I'm here, so they should come and see
We're
me.
very honored and grateful for you spending your time here.
But thank you. It's been a pleasure to be with you.
We can't wait to find more discoveries together.
Let's
Thank you.
hope so. Thank you.
Bye.
The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
you.